All right. So, yeah, so now we will have two more lectures. Today, I'm going to discuss the okay. So one lecture and one hands-on session. So today, I'm going to discuss the cosmic microwave background. So is we left where we said that the inflation, we start with a sub-Hubble initial condition, and we revolve the curvature perturbation at the super Hubble scales, and then it remains conserved till the end of inflation. So we just say that we can stop the integration there. And what are these curvature perturbations? They're actually related to the metric perturbations, right? So R is a function of the Bardeen potential that you see in the metric, and there we didn't have this anisotropic stress. Therefore, we didn't have any, actually, because of the absence of anisotropic sources, we didn't have any anisotropic stress, and we could only work with one particular scalar perturbation. What we'll see that if you make a generic formalism, general formalism here in the CMB, since there are interactions between photon and baryons and gravity. And there are interactions like dark matter, which interacts to gravity, and protons and electrons, etc., through Coulomb scattering, and photons and electrons via Compton scattering. We have to keep a generic form of the metric, and then we will see that how these metric perturbations are imprinted um, on the anisotropies of the temperature. Okay, so we'll calculate the anisotropies of the temperature in the recombination of the last scattering surface, on the last scattering surface, and then we'll see that how they free stream towards us, and then we can map it in the in today's plane, in today's sphere. Okay, that we can observe. Okay, the thing is that cosmic microwave background is a pretty, I mean, big topic, so we cannot actually hope to cover all the aspects. So what I'm going to do is that I'm going to start with a very I mean, pedagogical or popular level, and then slowly go to the main aspects of the theoretical formulation of the cosmic microwave background. And then I'm going to talk about, I mean, those things I'm going to discuss in the Jamboard. I will not be doing all the derivations. I mean, I'm just going to give you the roadmap, that how, for example, you solve the Boltzmann equation, why do you need the Boltzmann equation, etc. I'll write the key equations, and then I'll show you what are the main features in the cosmic microwave background observations. For example, at large scales, what are the observables, for example, in the CLs, for example, different part of the CL, right? You have seen from the map, you can take the average of ALM in I think Professor Twin Ghos's lecture, and get the cosmic microwave background and angular power spectrum. In the angular power spectrum, you have seen that there is some kind of plateau at the large scales, that means low L. Then there are oscillations, and there are these damped oscillations. I'm going to discuss what each part of these oscillations represent in terms of theory. And then I'm going to discuss the Planck likelihood, okay, that takes the data and creates a likelihood, so that if you supply that with the data, with the theory, with a particular theory, how you can constrain that model. And after that, using mainly, I'll discuss the Planck likelihood. I mean, earlier there were WMAP likelihood, etc. You also have small scale likelihood from Atacama cosmology telescope, etc. But I'm not going to discuss those. I'll discuss mainly the part of how the Planck likelihood are broken into large scales and small scales. What are the frequency channels? What are the foregrounds, etc. Again, I'll just touch upon those topics. I'm not into the detail of the foreground, how the foregrounds are calculated. I mean, some of them are actually beyond my area of expertise as well. And then after that, I'm going to discuss what are the present constraints. Okay, what are the present constraints on the cosmological parameters, how you can arrive at the constraints. After that, I'm going to discuss what are the problems in cosmic microwave. What are the okay, I shouldn't say problems in the cosmic microwave background, it's just the tensions between the results obtained from the cosmic microwave background and other results obtained from, for example, astrophysical observation, etc. After that, I'm going to discuss what is in the future, how you can, I mean, what you can project from upcoming observations. Anyway, I hope to cover all these in today's lecture. I hope that it will be done within 2 hours. Okay, so first 30 minutes, I'm going to discuss some things from my slides, and then I'll take about 1 hour, I hope, to discuss the do the calculation in the Jamboard. After that, I'm going to switch over to the slides again. Okay. All right. And tomorrow's lecture are going to be on the calculation of numerical computation of the cosmic microwave background angular power spectrum, and certain constraints not from the Cosmo MC, because we cannot run Cosmo MC in this time frame. You need about 6 or 8 hours. I'll let you know how to do that. We will also install the Planck likelihood as well. We'll get some constraints on the reionization history, just to show you something on the cosmic microwave background, how you can get the constraints from a summary statistics, from the statistics of tau. Okay, and then we'll see what are the different effects on the cosmic microwave background from if you change, let's say, the history of reionization, if you change primordial power spectrum, if you change baryon density, or if you change dark energy equation of states, etc. Okay, so as you can see that this part is actually interconnected with all the subjects that you are learning. Okay, for example, dark energy, and also it is interlinked with the large scale structure, definitely. Okay, so let's start. Okay. Okay, there was one question. Okay, so it's a note from Supradikta. So let me start with this brief history of the universe, the timeline. For example, we had already discussed the cosmic inflation, where the seeds of the structure formation were originated from the quantum fluctuations. Okay, and then particles form, and then it is the radiation dominated era, and then after that the universe expanded and then cooled down. At the same time, the hydrogen, electron and proton electron and protons combined as soon as the mean free path of the photons increased, so that it cannot knock the electrons out of the hydrogen atom. So that part is called recombination. And then after that, during that, at some point of time, we'll discuss what point we say that this is the epoch, epoch of decoupling. At some point of time, the photons decouple from the matter. So then we have this matter dominated epoch where the structures form, and today now we are in a lambda or dark energy dominated epoch. Okay, so let me just show you one very important video. If you have not seen already, this is how the observations are made. Probably you have seen this, but let me show you anyway for the students who haven't had a chance to see it. So this is a animation of Planck satellite. So you send the Planck satellite to L2 Lagrange point, the second Lagrange point, and it basically looks at the sky and takes the map of the universe at the microwave frequencies. So Planck specifically had 9 frequency channels. You already know that. And the red part, I think you also know that this is something known as the Milky Way, the effect of the Milky Way in the cosmic microwave background. And you mask that out in order to get the CMB right? You can use different types of masks. And, all right. So in a projection, the cosmic microwave background looks like this, and this is in the visible region. And yeah. Yeah, that's it. And but what you see in actually, if you just get the map, you will see that there is a uniform temperature. Okay, the uniform temperature is 2.7255 Kelvin that I discussed when I discussed the horizon problem. Then there is this dipole because of our motion with respect to the CMB. So one part looks hotter and one part looks colder. Okay, so it is the Doppler effect. And then if you just remove that, this is of the order of, so this is of the order of Kelvin, this is of the order of millikelvin. And when you subtract that out, you will find the cosmic microwave background anisotropies that are of the micro Kelvin order. All right. And somebody has asked me that we have more and more fluctuations, and I discussed that no, there are not more fluctuations. The thing is that the fluctuations are smoothed out if your resolution is not good. So this is from Kobe and this is from WMAP. Okay. Okay, so the spectrum of the CMB, how does it look like? So we know that above the ionization temperature, hydrogen could not be formed. They had strong interaction with radiation. Actually, even below the ionization temperature, 13 point or energy 13.6 electron volt, the hydrogen could not be formed because of the strong coupling. And actually it happened in a lower temperature, at a lower temperature. We're going to discuss that. And there when there was scattering between photons and matter, they were in thermal equilibrium. After the photons stopped interacting with matter, so when the mean free path increases, they started streaming freely to be received today as the CMB. And the fluctuations in the CMB traces the fluctuation in the spatial distribution of matter at that time. Okay. And as you can understand, why we say that this is the inflation puts the seed of the structure formation, because now we see that these are the stresses of the spatial distribution of matter. Later on, when the universe evolved in the matter dominated epoch, so spatial distribution, where there were more matter, they clumped together and started forming galaxies, clusters, etc. Okay,